Good morning. Now we're going to see the formulas which is needed for us to convert analog filters to another analog filter. Why we need this? Basically, we know formulas to design normalized low pass filter. What do you mean by normalized low pass filter? Normalized low pass filter is one wherein omega p is equal to 1 radians per second. But in general, omega p value need not be 1 radians per second. It could be something else. But we know formulas only to design normalized low pass filter wherein omega p is equal to 1 radians per second. As a result, in general, whatever may the value of omega p, we first design or will obtain transfer function for normalized low pass filter, and then with help of suitable transformation, we'll convert normalized low pass filter into desired filter. As you can observe here, there are three columns. In the first column, we have written prototype frequency response. Here, if you observe, they're all one and the same. That is, x-axis is always frequency axis, y-axis is magnitude axis or gain axis. And if you observe, here you will get two values. One is kpks. Corresponding to kp, we have omega p, and its value is always 1, which is nothing but, that's what I mean by normalized. Corresponding to ks, we have one more frequency, that is omega s. This could be any value. So if you observe, they're all one and the same. Even the second row is same. If we compare second row with third row, this diagram remains same. Similarly, the last one will also remain same. Whereas if you observe second column, here this is my frequency response for low pass filter. This is frequency response for high pass filter, and then frequency response for band pass, and then frequency response for band stop. And third column indicates backward difference equation. I'll discuss about this little later. So as I told, in general, I know formulas only to design this one, that is normalized low pass filter wherein omega p is equal to 1 radians per second. But in general, most of the times we won't get omega p or omega u as 1 radians per second. In that case, we first design this, then use suitable transformation, which is this, to convert normalized low pass filter into a desired filter. That's what we can understand from this particular table. So what is the transformation then? The transformation is for the transfer function that what you obtain. In general, as I already mentioned, when we design analog filters, the transfer function is always in S domain. So there, in that particular transformation, S has to be replaced by S by omega u. In general, it is for analog to analog transformation. But for Butterworth, it is like this. S has to be replaced by S by omega c. Here omega c is nothing but cutoff frequency. Here omega u stands for upper cutoff frequency. If you do this, you can convert normalized low pass filter into a desired filter. Suppose, assume that if they gave you this, that is omega u, omega s dash, you want to get back this. That is, in general, omega p will be 1 radians per second, but you want to obtain omega s. That is, you want to convert desired filter into normalized. Then what is the formula I need to use? I need to use this particular formula. That is, see, kp, ks, y-axis will remain same, right? When you compare this with this, they are one and the same. Here, omega p is 1, of course, for normalized, but we need to find out the value of omega s, which may not be given in desired filter. So if you want to obtain this particular value, then use this particular equation, that is omega s is given by omega s dash divided by omega u. Then you can convert desired frequency response to normalized one. That is what is the meaning of backward difference equation. Hope you have understood. The same principle applies even for high pass filter. That is, if you want to design high pass filter, then design normalized low pass filter wherein omega p is equal to 1 radians per second, then use this particular transformation, that is S has to be replaced by omega u by S. This is for analog to analog transformation, remember this. For Butterworth there is slight change, we'll check that when I discuss about that particular problem. If you want to convert this, that is normalized low pass into high pass, then this is the transformation you need to use, or S has to be replaced by omega u by S. As a result, you will get desired high pass filter where y-axis remains same as this, whereas x-axis there are two changes. One is omega s dash and omega u. Suppose assume that they will give you this, you want to get back this, then use this particular formula, that is omega s is given by omega u by omega s dash. As a result, you will get back this, that is normalized low pass filter from desired high pass filter. The same logic applies even for band pass as well as band stop filter. We'll check the formulas. So in general, if they gave you to design band pass filter, then first design normalized low pass filter, then use this particular transformation, that is S replaced by S square plus omega u omega L, upper cutoff frequency lower cutoff frequency into S into omega u minus omega L. This is the general specifications for a magnitude frequency response, where in y-axis it is kpks, that is pass band as well as stop band frequency. Since this is band pass filter, for a one value of k you will get two values of omega, that is omega L omega u. Similarly, for one value of ks you will get two values of omega, that is omega 1 and other one is omega 2. Suppose if they gave you this, if you want to get this, then use this, that is omega s is given by minimum of magnitude A, magnitude B. What is A and B? A and B are given by this, that is A is equal to minus omega 1 square plus omega L omega u divided by omega 1 into omega u minus omega L. Similarly, B is given by omega 2 square minus omega L omega u divided by omega 2 into omega u minus omega L. So you'll get some value for A and some value for B. Take magnitude of it, whichever one is less, that will be the value for omega s. That is the meaning of this. As a result, you will get this particular one, which is normalized low pass filter. Same principle applies for band stop filter as well. So if you want to design band stop filter, so in general we are going to design normalized low pass filter. The reason is we know formula only for this, and then use this particular transformation, that is S has to be replaced by S into omega u minus omega L divided by S square plus omega u into omega L, so that we can convert normalized low pass filter into band pass filter, where band pass filter specifications are like this. Y-axis kpks, corresponding to kp we have two values, one is omega L, other one is omega 2. Corresponding to ks we have two more values, they are omega 1 and omega u. Suppose if they have given you this, if you want to get back this, then use this particular formula, that is omega s is equal to minimum of magnitude A, magnitude B, where A is given by omega 1 into omega u minus omega L divided by omega 1 square plus omega L omega u. Similarly, B is given by omega 2 into omega u minus omega L divided by minus omega 2 square plus omega L omega u. So find out this value, find out this value. Out of these two values, whichever one is minimum, that will become the value for omega s. As a result, you can convert desired band stop filter into normalized low pass filter. Hope you understood the importance of this particular table. Thank you.